Hello, everybody. So we are back at class 6, and we will be talking today as per the syllabus, and I'm sharing my screen right away that I'm not forgetting this again. As per the syllabus, we're going to be talking today about statistic inference for linear models, p-values in this context, the likelihood ratio test, model diagnosis in terms of non-normality, non-constant variance, and non-linearity. Good. So let's quickly get started. And I hope things are going well. I think all have been explained sufficiently. So we will also be reviewing the CITES paper that will be part of the lab. And so this will be posted separately. Then please remember that next week homework 1 is due. So this is before class you can ignore. So the deadline is essentially on 10/11. And research notes will be assigned. And we will continue on the conversation next week about linear regression, covariate handling in RCTs. Please also make sure that you are aware of the exam, which is going to take place on 10/18. I will be posting this exam, and you will have that week time to take the exam. And we will then on 10/25 continue with lectures. So, this all being said, let's go and get started with things. So we have posted the, oh no, not the lab file. So here's our RMD file. Just like always, please go and knit it into a PDF. For those of you that do have had troubles installing the MikTeX, please just knit it as an HTML. I will also post the PDF version to the Blackboard that you can review the PDF file and make sure that you're keeping on track. So the HTML does have some problems in terms of the equation. I've noticed now the other day, and I'm not really sure why that is. It's very hard for me to understand, to be honest. I must have something to do with the process of the knitting method. I don't know. I'm not that much of an expert on these aspects. However, most of you seem to have no problem with knitting into PDFs. Good. So this is now happening. It's going to take a little while. Back to lecture. No. Class 620. There we go. Okay, so it's about to wrap it up. So all the dependencies do have to be copied in the same directory. I hope there were no problems along these lines with this approach. There are quite a few figures this time, so please make sure that all of these are contained in the same folder. Okay. This is now ready. All right. Okay, very good. Okay, so I can post this now. It's going to wrap it up. Okay. So here you see these are all the, this actually goes into the lab. Okay. All right, so now let's open the PDF. Here we go, that's the PDF. So class 6 on October 3, that's today. It's actually should be October 4, but okay. All right, so back to applied biostatistics. Today is October 3rd. We will be talking today about statistic inference of the beta, the regression coefficient. We will be discussing the standard error for the point estimate. We will be discussing p-values and the interpretation in the context of regression models. We will also talk about the residual error and the interpretation and the assumptions made and applicable to the diagnosis of residuals. We will also talk about the diagnostic analyses that can be conducted. This will include non-normality in the data and the residual error, non-constant variance, which is a very important topic essentially, and non-linearity. I would like to emphasize that these diagnostic procedures and the way how to approach them will be part of the research note. So you will be expected to essentially discuss that in the research note and to address this appropriately in the research note. So we will then also do lab 6, which contains univariate and multivariate analyses and also includes model diagnosis. Okay, so we have talked the last time about assuming a Y essentially is obtained from two groups. We have as a possible choice of these two groups, it could be gender, could be male or female, and this comes from survey data or some form of a research study. So he's saying essentially we have here YI and YJ. So YI essentially is values that can be I from 1 to K, which is the sample size in group 1. And then we have YJ that essentially can be where J can take K plus 1 up to an N. So essentially we can now assume that we have, okay, so K plus 1, what does K plus 1 mean? So I hope all of you have noticed that we have here 1 to K. So this is our reference group. This is where X equals 0, 1 to K. And now we have J basically constitutes arithmetically the second group, which is basically K plus 1. So this continues from here, K plus 1 to a total of N. And N is the sample size of the overall population. So just to make sure that we're on the same page with this, here we have the mu 0 and the mu 1, which essentially is the mean in group 0 and the mean in group 1. And then we have here the variance, which is considered to be identical for both groups. And then we have yi, which is I 1 to K, and yj, which is j K plus to N. So this basically constitutes these kind of like participant IDs within the two groups, right? Where N is the last individual. So if there are 100 people, N would be 100. K would be, if it's identically sized, the two groups, K would be 50. So recorded for a two-sample t-test, we focus on the difference between the sample means. We remember the t-test. If it's a two-sample t-test, we're drawing independent samples from each group. And these samples basically constitutes, we calculate the means. So we're calculating and not infinite, but a large number of means. And we get a distribution of the sample means, and we're comparing with an independent sample t-test, we're comparing these two groups by comparing the distribution of means of all these independent samples that we've drawn from each individual group. So this being said, we are essentially now estimating the y bar 1 from that group minus the y bar 0 from that group to estimate this mu 1 minus that mu 0. To essentially calculate the so-called t-score, which you remember from introductory statistics, is essentially then reflecting following the t-distribution, where you estimate your standard deviation and your mean from the sample mean and sample standard deviation, and you assume this is the same in the population. You essentially divide the difference between y bar 1 and y bar 0 by the so-called pool standard deviation, or the pool standard error, essentially, which is calculated in various ways. You have the aliquots according to the sample size, and you essentially, you're testing by that, you're testing the difference between y1 and y2 under the null hypothesis that y1 and y0 is identical, it's the same, it's similar. So standard error is this SE, and this will allow you to essentially calculate the T out of your difference. And this essentially is the difference in conceptually, that's the difference of these sample means, of the mean of the sample means that you have drawn. And you're assuming you take out one sample, and you assume the sample is representing the overall population, you're comparing this sample mean that you have at hand, and you're assuming that this is the same as the mean of the means of all your independent samples. And then essentially with the standard error, you're essentially using the standard deviation that you have in your samples to estimate. So standard deviation divided by a square root of the n gets you the standard error of each of those groups, right? You do this pooled standard deviation. You calculate for the independent sample t-test this pooled standard deviation. You get an aliquot pooled standard deviation representing each group's sample size. And so that the 1 to k and the k plus 1 to n. And by that, you get a pooled standard error. And this is the pooled standard error that you use to divide your difference by. This gives you the t-score in an independent sample t-test. So now moving over to basically come to a regression model, essentially is now going towards yi is beta 0 plus beta 1 xi. And here xi is essentially either 0 or 1 plus a residual error for all individual in the overall population, sample population. This error is considered to be normally distributed around a mean of 0 with a variance sigma square. This again includes the entire sample population, where beta 1 essentially constitutes of the difference between mu1 minus mu0. And we have talked about this the last time, right? So you're taking the reference value, you're taking the mean of the reference value, and then you add the coefficient. This is our intercept plus the error. And then we add the coefficient multiplied by 1 to get to the yi group. So we remember that from the lab last time when we calculated the essentially values for the blood pressure. So testing now mu0 is equal to mu1 is equivalent to test beta 1 equals to 0. What does this mean? So essentially this difference is identically if the null hypothesis is not being rejected. Equally, if the beta 1 is not significant, you would also assume that there's no difference between the groups. So this is essentially where a regression model can replace, almost replace, not just always, can replace a t-test. This is also the reason why you see in the model output a t-value. This t-value essentially is nothing else but a t-value that you would yield from a t-test. It's going in the same, it's doing essentially the same analysis. So what we're doing, so we have seen this this output. So we have 1 plus x, we have minimal value of the residuals, we have maximal value of the residuals, we have the Q3 and the Q1, and we have the median. So median, why is the mean not stated here? Because the mean is arithmetically 0, meaning these residuals shape around a mean of 0. If the median is different from the mean, what does that mean? It means that there are essentially outliers that have shifted the mean away from the median, which is in that case here not as terrible as it probably could be in different contexts. So now we have the coefficients, we have the intercept, which we know is here 228, which is a rather unrealistic example, but we know that already from the previous exercise. Then we have the sex, and we have a standard error for sex. We have a t-value, and we have a p-value. What do we see here? we essentially see that sex essentially results in a smaller blood pressure as compared in the Y1 group as compared to the reference group. So now we have the situation that here, we can test this. Actually, look at this. Let's go to the RMD file. So we have here sex, our binom 1 and 0. It's not defined which one is which one. So let's, okay, there's a significant difference with male and female, yes. Okay, good. So it's not defined, it's a simulated data set, so it's not defined, but that's fine. But essentially the group X equals 1 is essentially at this point the one which has a lower blood pressure. So the reference group, this is male, which is unlikely it would be female because males tend to have higher blood pressure, as we know. So the reference group essentially has a higher blood pressure as compared to the other group. So it actually, the reference group would need to be male, assuming that my statement that females have lower blood pressure is correct. Good. What else do we have? So as for the rest of those parts of the printout, we have talked about this. We have the residual standard error. We have here 4.92 and 98 degrees of freedom. We have a multiple R squared. We have adjusted R squared. We have discussed all of this. Note here, and this is, I want to flag this because this comes up quite often. I actually see that a couple of times now in my own line of work. So R squared is arithmetically always positive. It has to be because it's basically the explained variance divided by the total variance. It has to be, right? It's a ratio. It's a ratio of something that can never be negative. However, if you penalize your R squared, and I refer to the introductory statistics, which essentially I have showed you how to calculate an adjusted R squared. In this setting, for the penalization of the number of covariates included in your model, R squared can turn negative. So please, I'm flagging this, keep this in mind whenever it comes up, adjusted R squares can be negative. And this is even true in Excel, where you, by default, if I recall correctly, always get an adjusted R square. Then we have here the F statistics. The F statistic is basically assessing overall the accuracy of the model, whether there's actually a significant covariate included in your model, and basically shows it on an overall, how should I say, an overall unimodal right skewed distribution, which essentially is following a one-sided hypothesis, meaning if the F exceeds one critical value of 5%, which is dependent on the between group and within group decrease of freedom, meaning the number of groups that you're testing and the number of entries or cases within all groups, this critical threshold is determined. So if your F essentially exceeds, so this is the between group degrees of freedom, this is the within groups degrees of freedom. So we have 100 males and females in two groups. Degrees of freedom is 2 minus 1. Total degrees of freedom is 100 minus 2 groups, 98. So we have 100 individual in there. The p-value is 0.8034, and this essentially we are right now confirming here arithmetically, and this is an interesting exercise. So here's the t-value for beta 1. So we know that our sex estimate here is minus 0.213. Dividing this by a standard error, which we could hypothetically not quantify, we could calculate the standard error by quantifying the standard deviation, and which would be the individual entry minus the mean. We're basically getting all these deviations for each case from the mean within the group, notably. Then we get a square. We're squaring this deviation. We get squared deviations. We're summing the squared deviation. We get to the sum of squares. From the sum of squares, essentially, we are dividing it. We're getting to the standard deviation. From the standard deviation, we get to a standard error of the mean by dividing the standard deviation by the square root of the n. That's how we get the standard error. And this gives us for minus 0.2129, we're dividing this by 1.149, which is here. We're getting to minus 0.21. This is, as said, our t-score. And this t-score can easily be, and I just want to show this quickly. Let me quickly show you this. You all have seen in statistics, in introductory statistics, you all have seen the t-table. So you know, essentially, I'm just taking it up from different class. We should find it from one. No, just a second, sorry. I'm finding this. Okay, when you really want to find something, you never find it. This is for the lunch. Okay. I do literally not find it. Oh yeah. Okay. So t-score table, just as a recap. So the t-distribution table, and this is basically where you find these values, right? So we're looking for what are we looking for? Minus 0.21. Minus 0.21, right? Too many windows open. Okay. So this. Okay, now I lost my PDF. Okay. Okay. Okay, we're looking for minus 0.21. Yeah, so back. Minus 0.21 is essentially with a sample size of 98, degrees of freedom of 98. Minus 0.29 is here substantially smaller than what the critical threshold would be. So we would need, so here we see one tails and two tails. So we are testing. That's absolutely not what it was. This is absolutely not the right lecture. Oh boy, too long I do this to make a confused professor. Okay, I have it in a second. In class BIOS6 lecture. Okay, here we go. I'm not sure why I closed it. Oh, that's why it was a different screen. Okay. Okay, so now we have this back. Okay, good. Estimate divided by standard error. This is our t-score. We get a t-score of minus 0.21, which in that case, because it's two-tailed, doesn't really matter what the size is. But what we see clearly from what we're doing is like if we're multiplying this by 2, we are essentially looking. Okay, so we do not have this actual value. We just thresholds because we're looking it up in a t-score. in a t-square table. So it would be 0.417. If we look here at our critical thresholds, and these are the thresholds, to achieve a 5% p-value that would lead to significance, we would have needed at least 1.99, right? Or more, 1.98, somewhere in between. So this is essentially these t-square tables give you the critical threshold. If you don't exceed them with your estimate of the t-score, you will not reject the null hypothesis. Good. This being said, we are not rejecting the null hypothesis. We're getting a p-value of 0.834, which is obviously not significant. Okay, n equals 100 to parameter. If the p-value is less than 5%, we would state any of these. If it were less than 5%, we would state that sex is significantly associated with SPP. Is yes, is a valid statement. There's a significant difference between males and females with respect to SPP. Yes. And males tends to have significantly larger SPPs than females, which essentially implies here that males have been the reference group, because females, which would be x equals 1, would have a smaller SPP. Good. So this was this. So how can you further this exercise? How can you further the inclusion of additional covariates, particularly one as complex as our EDU factor? And how can we confirm that EDU in general, independent of the grouping, independent of the categories, is significantly associated with SPP? So we're having now our model. Our model includes, in addition to the intercept, it includes age, it includes sex, and it includes our EDU parameters. So we remember no high school, and college. So now we have to use a little bit more of a complex method here, which is to some extent, it's in its basis, it's somewhat an ANOVA. And in this context, it's referred to as a likelihood ratio test. So essentially, we're doing now a comparison between our two models. So we have model number one. Model number one is SPP as the response variable. We have 1 for the intercept. Remember that -1 would suppress the intercept. So we do +1, plus age, plus sex. So this is our base model, right? So in the very basis, we only used sex as the example of what constitutes the t-test. But now in model 2, we're using the same model. We're again including the covariate, age and sex. But in addition to that, we're including EDU as a factor. As a factor that we have here defined that not high school, not having completed high school was the reference category, because only those that are not the reference category actually listed in the output. So essentially we are including this factor, and by that we're getting here, so we're getting residual degrees of freedom. We're getting a regression sum of squares, which essentially gets up to an overall sum of squares of the difference. And this will allow us to quantify the F value. And this F statistic allows us now to do what I referred to before in the ANOVA, right? This is essentially what one model does. And in the comparison of both models, you do the same thing. So you're comparing the regression sum of squares, but basically summing your sum of squares. By that, you're getting to an F value. And by that, you get to a p-value. And this p-value is read from an F table, which I can show you as well. I think it's always nice to see these tables, because they kind of give you a handle on how things look like if you wouldn't do them with fancy statistical methods. And it kind of, personally, I think it helps to kind of get a little bit of a better insight into this. I hope you agree with me here. I personally, I believe in that kind of it. But again, the same issue. I don't find my tables. Here we go. Okay, so now I know what it's at. Okay, so we have here F-score table. So just for you to see what this F statistic looks like. So we are doing, essentially, we are calculating the regression sum of squares for each of these. We're calculating a difference in sum of squares, which is here 366, right? So 4359 plus 366 is 4726. So this difference of the sum of squares is what you're essentially dealing with. And this is where you have your F, you have your degrees of freedom, which is 2 groups, right? So you have here a residual degrees of freedom. You have 97, you have for model 2, you have 95 because there's some dropping off. Essentially, you get here the degrees of freedom of 2 for 2 groups. Oh, no, for the covariates. Sorry, it's not the groups, it's the covariates, because you have 3 covariates. You have 1, 2, 3 covariates. Sorry for that. Now it has to be, because this is essentially these are degrees of freedom from the residuals. We do not have these residuals at this point in mind anymore because we're comparing the models. Okay, sorry for that. Now it's 3 covariates. We have EDU, age, and sex. Degrees of freedom is 2. So this becomes our between group degrees of freedom. So now it's, we have now the between group variability divided by the total variability. So essentially we have here degrees of freedom in the numerator. This is our between group variability, and this is in the denominator. This is our overall residual degrees of freedom. So we have 95 and we have degrees of freedom of 2. So essentially we would find our significant threshold p-value here on this so basically on the columns we have the between group. So this is 2. This would be here, that would be the second column. And now we're going for the denominator. We are looking now for 95. So our critical threshold here would be, yeah, somewhere in this realm, second column. That would be somewhere in the realm of p-value of 5% of 3.09. So now with an F of 3.989 or 9999 or 9895, we are looking at a p-value of 2%. And this is non-calculated. So this is found in this F-score table. Good. I hope that kind of made sense to kind of ramble out here a bit. Okay, so EDU is significantly associated with the outcome p-value of 2%. So I hope that was somewhat clear, and please go through that. Look at the F-score tables. Go through the background of all of this. This will be important knowledge also for the exam. So statistically significant versus practically significant. And this is in this context quite important because when you're looking at the difference that we have seen between the blood pressures in males and females, this is 0.2 difference in blood pressure. 0.2 difference in blood pressure is essentially super marginal. So what you will need to keep in mind here is that just because you have a significant difference, this does not mean it's actually any meaningful difference. So for that very reason, we essentially we essentially need to keep in mind to always look at the meaning and the actual relevant difference. So if we would find a significant result, you also need to understand where is this result coming from, what does this result actually show, and to what extent is this really relevant in clinical practice or in any other practice. The problem with that is that significance per se will arithmetically always be dependent on the sample size. And when you keep in mind how we calculated the t-score, part of that t-score was the division of the difference by the standard error. So the standard error is the distribution of the sample means, so it's actually the variability of the means. But equally for the standard error as well as for the standard deviation less so essentially because it's still a raw value, but for the standard error quite pronounced because you're dividing it by the square root of the sample size. You will lower, or you will make the actual variability in that context of the standard error, the variability of the sample means narrower, smaller. As a consequence of that, you will be more likely to achieve statistical significance. Does that mean this is a super great result that by all means needs to be spread to the community? No, because you need to understand what the difference actually means. If this is a blood pressure difference of 0.2, the scientific merit can be debated. Okay, so you get statistical significance of a fixed difference by increasing the sample. This is exactly what I said, because you make the standard error smaller by dividing just by a larger number in the denominator. Okay, let's go back to full screen. All right. Significance. Okay, the multiple linear regression is essentially now in the same fashion depicted as the single linear regression or the simple linear regression. There's only one covariate, which is univariate regression. It's essentially, it's nothing else but including more and more, adding more and more covariates to the model. Equally, we are looking at residual error. That is the same, which is essentially I, which I can take values from 1 to n. These are independent entries. So this is not yet a longitudinal model where you have repeated measures. This will be part of BIOS2 of your next step in statistical education. And they are meant to be identically distributed. This distribution of this error should be normally distributed around a mean of 0 and a variance of sigma square. We're interpreting this as a measurement error of yi, and the effects of other factors are not included in the regression model, which is one of the problems, because this will then essentially drive your residual error. So these other factors can be included as covariates. So it's actually, or potential covariates are not included yet. Again, for multiple linear regression, we have yi is beta 0 plus beta 1 x1i to xp beta p xpi plus this residual error. And there are a couple of assumptions that you have, which are to some extent not entirely different from what we assumed before for the simple linear regression, for the univariate linear regression. So we are assuming that the distribution of the residual error is normally distributed. Yes. We assume that the mean is of this residual errors is 0, which is also part of what we've just discussed before. And now we're coming to a very tricky part of it, because now we're discussing the constant variance. So the constant variance means that this error is not only normally distributed at an error variability that essentially has to be identically and symmetrically shaped, as we know from the bell curve. Also, that this has to be constant, a constant error, a constant variability of that error over the entire range of magnitudes of the measured y, of the predicted y. So now, so notably the y, the response variable, right? So now this is called homoskedasticity. Homoskedasticity is quite commonly found as an assumption, and we will see that again in various other contexts. Further, we need to keep in mind that the residual error of J and the residual error of K, which are basically our, so you remember the 100 males and females are like the first 50 are the men, 51 to 100 are the females with the smaller blood pressures. So this residual error needs to be independent of purely the difference between those two groups. So it's not something that needs to be attributed to just these differences between the groups. So this is the fourth assumption. Yeah, so we know that the normal distribution has the following properties. We know it has to be systematic, it has to be unimodal, it has to be symmetric. Yeah, okay, so it has to be symmetric, it has to be symmetric, and it has to be unimodal, and it has to be bell-shaped. This essentially is the classical form of the bell-shaped curve as described by Gauss. And this essentially allows us to diagnose this as a normal distribution. So the question is, what are we going to do if this is not normally distributed? Are you just not going to do the analysis? Well, you still will try to do the analysis, right? So if you have a skewed error, this compromises the interpretation of the least square regression, because we could rewrite this then essentially into a different shape, where essentially the covariance will be impacting the mean of the yi. So that means that if you're trying to predict your yi, and you have a skewed covariate in there that essentially at some certain magnitudes or some certain parts of the entire range of data suddenly shows more of a skewed data, this will affect your estimate, right? And just as a recap again, what does that mean? So if you, for example, if you have a negative skew, and this is also about this distribution of the residuals is so important, right? So you have the mean and the median. The mean is 0. The median, if the median exceeds a certain level of magnitude, you need to be quite aware of that, and you need to look at this data in more detail. So essentially, if you have a mean that is driven by a couple of outliers here on the left side, so it's negatively skewed. So you essentially, you see that the mean is being pulled to the right, to the left, sorry. The median will also be pulled, but only a little bit. So it's the median is more resistant against those outliers, whereas the mean basically will arithmetically have to follow those outliers. Equally, positively skewed, yes, and the mode, and this is quite obvious when you think about the definition of the mode, because the mode is the most often occurring number or value. So this is unimodal in your Gauss distribution curve, right? Where if it's perfectly symmetric, you have mean, median, and mode basically at one point. If it's positively skewed, you have the same situation just to the right, and basically it pulls to the right. Okay, so this is this. So if you have skewed data in your model, this will affect the accuracy of your estimate and will result in a skewed estimate. So this is this. So now we have multimodal distribution. Multimodal error distribution indicates the missing of important covariates, which could naturally divide the data into different groups. And this is a little hard to deal with, right? As you can imagine, this is not an easy one. But you can deal with it classically with stratification, and we'll talk about this. I mentioned it a little later. So essentially, you have to deal with it somehow, and stratification is the easiest way forward. So we have a heavy tail distribution. We're comparing with a bell-shaped normal distribution. Heavy-tailed errors with very strong outliers makes the standard error of the better head inaccurate, which is unfortunately one of the downsides of these statistics, sometimes unavoidable. However, it's important to be aware of it to make then essentially down the road sensitivity analysis that confirm what you want to confirm and that actually make sure that you are on the right track and you yielding valid interpretations. So non-normality, how to check, how to correct. So essentially non-normality here, the histogram of error basically shows the extreme outliers and on the QQ plot. And you have on the QQ plot shows essentially quantiles, which are the actual quantiles from the sample as a function of theoretical quantiles. So this essentially will show these residuals and allows for you to determine the shape of the residuals. So how do these residuals really compare to theoretical quantiles? So if you had a normal distribution, you would be looking at a distribution like that. There will always be some deviations from the line of identity here, but overall you see something that is much more evenly distributed. Whereas if you look at the theoretical quantile and sample quantile differences here, so the theoretical quantiles how they would look like in a perfect world, right? So comparing the sample quantiles to these theoretical quantiles essentially shows you here an extreme skew, which is quite obvious when you look here at the data. However, if you start to transform it, and there are various ways of transformation, logarithmic transformation as done here, one of the more common ones, you will essentially end up, you will basically succeed to kind of get your data more closely resembling a normal bell curve, so a normal distribution. And this will allow for you to successfully fit the model. So this is non-normality. This is so the way you're interpreting this is essentially by plotting it, looking at that error, looking at the QQ plot, and in case you find it, you will try transformation, or, and that's the very conservative approach, if transformation doesn't work or transformation is not reasonable for whatever reason, there are many reasons of that, because log transformed data is like good luck interpreting. If you need that covariates to be interpreted in a way, it's going to be very hard. A conservative alternative approach is to stratify. And this will essentially also have the advantage for you to essentially understand the shape of your associations and the direction of your associations. So you will basically find in your data, and you will pick up nonlinear signals, right? If they are nonlinear signals in terms of, I don't know, magnitude of one parameter, and you stratify them into, I don't know, like you can do tertiles or quintiles or octiles or deciles, you will, as a consequence, you will be able to pick up these nonlinear signals, because if decile 1 and decile 10 and decile 5 are substantially different and they show a trend within themselves or within the association to the response variable yi, you essentially will pick up these non-normal signals, and this may in itself yield a lot of important information that you can use to answer your research question. So I would definitely stratification when you're. I personally, to be honest, I think log transformation, I've done it, I've published, including log transform data. I would not recommend it for parameters that you are interested in. The interpretation becomes very complicated. Would rather put the categorization. Okay, second assumption. So we talked about, let's go back, let's recap the assumptions. So normal distribution, the mean is 0, the mean of the residual is 0, constant variance, homoskedasticity, and then we have yj, residual error j and residual error k are independent of j and k differences. Purely these two differences. Okay. So non-constant variance, so heteroskedasticity. So the opposite of homoskedasticity is heteroskedasticity. Sorry, it's a little bit of a tongue breaker. So in a standard multiple linear regression model, you have included your covariates and, oh my God, what happened now? Sorry, a minute. That was a double click. I have a sensitive mouse. Okay, so we have beta 1, x1i, and we're including more and more covariates until we are left with the residual error I. This residual error is independent, identically distributed, and distributed around a mean of 0 with a variance sigma squared. Non-constant variance will now have a problem, right? So this basically gets you into a problem, and I just want to show you this one slide how that looks like, just to make sure that you understand what that actually means. So you can plot everything out, and there are residual plots which we'll discuss in the lab that allow for you to visually inspect your data and make sure that you do make the right decisions on how to approach your data. So if you look here at unstandardized residuals, and you're basically comparing them to unstandardized predicted values. So you see variability here in these deviations, right? These are relatively comparable across the entire board. If you are comparing now this on the left with this on the right, you see that these are substantially different, right? But the variance here on the left part, on the lower values, is smaller than it is on the right part of the plot, in the higher values. So this is how that would look like. And this is essentially where you have heteroskedastic data, where the variance increases with increase of the actual value. So is that something that you will commonly find? Unfortunately, yes. You always need to check this if you want to be on the safe side. So there are formal tests how to test that. There's a Dicky. No. I think it was called the Durbin-Watson test. Yeah, Durbin-Watson test. There's a way to, okay, sorry, I have to Google it to make sure. It's not part of the lecture, and I don't necessarily think it needs to be formally, it's the same question as whether you want to formally test for normality or non-normality. You can do that by comparing mean versus median and then just visually inspect it and kind of make sure that the distribution is somewhat equally sized for Q1, Q3, mean, median. And like just approach it like as an estimate. You can of course you can also do a Lilliefors test, you can do a Kolmogorov, Smirnov, you can do what's the set test? Slipped my mind right now. So there are very popular tests that you can do to test for normality. The problem is, as always, sample size will always yield significant results, meaning they will always give you significant rejection of the null hypothesis, and the null hypothesis is that it's normally distributed. So it's sample size will not be on your size. It's on your side in this context. So essentially, normal distribution can easily be assessed by visual inspection as a comparison of the residual errors and the actual size of the distribution. So same with the Durham-Watson test, sample size will not be in your favor, but what you can do, visual inspection should give you enough insights. What we can, in addition to that, do constant variance. So what do you do now if you have heteroskedastic data? If you use least square methods, you're going to have a little bit of a problem, because the problem will be that if you have your beta hat estimated from a beta hat asterisk, the actual standard deviation of your data will be greater than what you will be essentially see. So the problem is, if you have heteroskedastic data, you essentially your standard deviation will always lean towards the greater value, right? If you, for example, if you see a slope, this standard deviation will follow essentially that variability that you see in the region of the higher. So a slope meaning like a significant increase in whatever value, which essentially would then result in an heteroskedastic situation. So if you say, okay, so I'm seeing this increase in blood pressure with age, and the heteroskedasticity that you will be seeing is essentially caused by this increase. So you will have variability that will be increasing following the increase of the value over time, over age, not time. So that means that your actual standard error is going to be larger. If you account for that, you try to get it smaller. So the problem is that this essentially larger standard error will essentially result in a smaller, and this is the calculation of the actual t-score, right? So we have here beta hat divided by standard error beta hat. This is the calculation of our t-score in the model and the regression model. So this t-score is going to be smaller than the one where you accounted for this heteroskedasticity. So when the t-score is smaller, your p-value is going to be greater. Remember, the t-score table goes actually larger t-scores, smaller p-values. Smaller p-values, more likely you're rejecting a null hypothesis. So if you have non-constant variance, and this is the problem with it, if you have non-constant variance and you're using a least square estimation, which you do in most cases, you will likely run into type 2 error. So you're missing differences that you should have caught. For that very reason, you want to have methods that allow you to get your accounted beta. So this beta hat asterisk. And one of these methods is the Huber-White robust method. So we will be employing it. What the method does in principle, it basically builds clusters within your data and your population. It uses an empirical kind of approach to estimate the actual variance. So now it's not a perfect method, but it's a suitable method that allows you to decrease your variability and get a more realistic estimate of your variability, and therefore allows you to minimize or decrease the probability of conducting type 2 error. This is how we will be approaching this. And so you have the code in the RMD file, and we will play around with that in the lab. So you have the library foreign, which essentially allows you to open this effort DTA file. You're putting this here in an FPE. You're cutting out different groups in increments of 10 up until, so you take 3 groups, it's 5, 15, up until max. Include lowest, labels is weak, moderate, and strong. And then you are building a model and change. So change as a function of setting, effort, and data with the library LM test, and saying to which you can actually use this Huber-White method, and you essentially can account for those. So how does that look like? And this is interesting when you compare it, and this is interesting to see, because essentially you have here the change in effort as a function of setting, effort, and the constant. If you use a regular model using the ordinary least square estimation, you're coming through 0.169 to 4.144. You're coming down to having comparable kind of estimates, except for setting. So there's a difference, and with the intercept there's a difference. And what you see is, like, while the estimates are comparable, they're the same actually, the standard errors change. And this essentially goes in that direction. So it basically accounts for this non-constant variance, and it basically takes it into account. And you see here in the F statistic, you see a significant difference in your estimate. Oh, no, that's actually not. That's no, actually refers to this model. Sorry for now. It's actually not the comparison. Should have been compared. Okay, standard lim is simple linear regression. We have now yeah, so we have a nonlinear estimate. We can now again try to kind of fit this into the shape and form. So you're trying to kind of find a function that resembles the shape of the data. So when you have nonlinear data, you're basically trying to find a function that basically allows to fit, quote unquote, fit the model following the data. And that would essentially allow you to still avoid the type 2 error that could come with nonlinearity estimates. Another way of doing this is to essentially categorize. So when you, for example, when you have data like that, and you're stratifying here then BMI by age in actual years, you're stratifying into mean BMI by 5-year age groups, you essentially also can fit the model with your groups, which essentially is essentially allowing you to kind of understand the shape of your data and of your association. So categorization, again, I see the advantage of nonlinear function and to also be able to kind of understand them in more detail. You also can do trend analysis where you essentially try to really dig deep into your data and to kind of get a better hand on it. But again, this is all things that you can try to deal with nonlinear data, and yeah, all of well-chosen methods. A more modern approach to that is using a generalized additive model, GAM. This is beyond the scope of this course, but it's also a valid approach. Note that I've made this note in the beginning. Checking and addressing non-normality is in a combination with non-constant variance. It was testing for heteroskedasticity and non-linearity expected in the research note. Good. So now analyses of help RCT as an observational study. So this will be what we will be doing in the lab, and I will post a separate. And yeah, so we're at the end of the lecture, and please post your question to the discussion board, and let's have a conversation about things that you would like to learn more about, discuss in more detail. All right, thank you for now, and see you in the lab.